Start. Hello and welcome back to Calculus 2. Section 8.9 on improper integrals. We get to hopefully do and see some really cool stuff here. We are going to have two types of improper integrals, and all of them are utilizing limit. So if you are having any issue with limits, please, for limits, go back, review sections 2.4, 2.5, and I believe it was 4.8 for L'Hopital rule. Let me just verify that one. No, 4.7. You can also use the study plan in you can use study plan in my MATLAB, right, to do random problems and practice these sections. So what are we talking about today? So this is what you need to review if you have issue with limits. Every problem tonight is a limit problem. So where do we start? Type 1, type 2. So I'm going to show what these guys are, and then we're just going to do a whole bunch of problems that involve limits and everything else. So for type 1 integrals, we are dealing with definite integrals and area under the curve. We are going to have the area, right? So this is a function, and we are looking to calculate the area, in this case from 0 to, let's say, infinity. So your integral is going to be 0 to infinity of, let's say that this is 3e to the negative x dx. What is problematic in this particular case? Well, you see that over here on this side, area is kind of leaking out, right? Because this e to the negative x is never going to hit and touch x-axis, right? So the question is, right, you are expecting to see infinite area, but it turns out that it's finite in some cases. So the way to solve these guys would be to replace the infinity with a finite value, say b, because it's the upper limit, right? It goes a on the bottom and b on top. So you replace that with b, and then you send that b in the limit to infinity. So you kind of trick it, right? So this would be equal to the limit when b goes to infinity of 0 to b of 3e to the negative x dx, and then you just solve that. You can solve you know how to integrate, I hope, right? And this is why I said any technique. This integral could be trig sub. This integral could be partial fraction decomposition, right? The only thing that we are learning in this lecture is that your limit could be infinity, and you have to install this limit. Now, what you're going to integrate, like this is pretty much what you did with tangent lines. To find the slope, you had to take the derivative. Now, derivative was product rule, chain rule, quotient rule, whatever you had, implicit, right? So now this is the same thing. There is a procedure of what we learn, and then whatever integration fits, it fits. So type 1 improper integrals are going to be improper integrals that have infinities in limits. So that's type 1. Type 2, much scarier. It has a vertical asymptote inside the interval for integration. And those almost always are infinite. And as engineers, you have to train yourselves to spot those. Otherwise, whatever you build is going to explode. It's a very simple. You design a battery that has that type of discontinuity in a charging cycle, you just made a time bomb anytime you put in the charger into the, right? Because what's area under the curve? Energy stored. What is the infinite energy stored in a short interval of time, right? So unless you are working on mathematics of detonation, then as engineer, you need to stay away, far, far away from type 2. See, type 1 is cool, because type 1, you just leave your charger plugged in, right? And you just, right? It's not adding enough energy for it to reach the critical infinity, right? Now, here is the type 2. Type 2 integral is going to be, let's say you have a vertical asymptote here, and then let's say you have this. And then you go from 0 to, let's say this is 6, and this asymptote is at 3. You are looking for area under the curve here, and just as the previous one, right, this is where it's leaking. So now you still have an issue, right? Because at this asymptote of 3, you have to work out the limit. So your problematic point could be infinity. Your problematic point could be, you know what, let's just do this, even if we do this just one-sided. You know what, I'm going to erase this and just leave one side for simplicity, okay? So what is my integral here? My integral is 3 to 6 of, I don't know, x squared, no. This is 1 over x minus 3 squared. There we go, much better. Dx. Do you see why this is so dangerous? Does this look like any other integral you ever did before? And the answer is yes. You can integrate this in your sleep. What is this? It's, right, u sub, basic u sub. X minus 3 is u, and you have 1 over u squared, and you integrate u to the negative 2, you get u to the negative 1 over negative 1. It's a joke, right? But look at your limits, right? Because you are going to get this as a negative 1 over x minus 3. And you plug in 3, you get negative 1 over 0. Now, it's not a problem when you integrate and your limit at the edge works out to be a vertical asymptote, because you are going to get 1 over 0 and you see something is wrong. How about if you had the other part here? So this is what engineers sometimes miss, and then we have note 7. So that's it. I make a joke, right? But that's what it is. Because if you integrate from 0 to 6, completely disregarding that there is this piece that opens it up towards infinity in the middle, or anywhere in between, can you compute at 0? Yeah. 0 minus 3 is just minus 3. Minus 1 over minus 3 is 1/3. Okay. Can you compute at 6? Sure you can. Minus 1 over. So you get 1/3 plus 1 over 6, and you're happy, right? Because you got a number. You build it. Why? Well, you missed the asymptote. The design had an asymptote. You didn't catch it. And because you didn't catch it, right, the infinite buildup of energy, right? Yes?
You would just catch a mistake like that by the simulated graph?
Yes, that's why simulations are important, because the computer is going to catch it, right? But you need to know where it's coming from, and you need to know how to fix it as engineering. It's your design. You're creating a battery that doesn't exist, right? You don't have an example to look up in the literature or something, right? You're making up a new thing. Pretty much everything in engineering is creating new things, right? So, type 1 is obvious that we can have issues, because you see infinities in limits, and infinities can, in this case, die out, or they can stick around, but at least they're visible. Type 2 is the scary case. So I say every time when I teach this lecture, this is your turning point in integration for life. Because from tonight, moving on, you always, when you have a definite integral, you know, the simplest definite integral that just goes from 1 to 2, or it goes from -3 to 7, across any of the fields, engineering, physics, whatever, just check if there is a vertical asymptote between these numbers. Because if it is, the integral is what we say divergent, meaning builds up into infinity. Now we're going to do examples and see that all of these things work out to be either finite, which is say convergent, or infinite, divergent. But these are the two types that we explore. So let's go. Oh, I should write limit a goes to 3, integral a to 6 of 1 over x minus 3 squared dx, and then use u sub, right? So these are the two introductory examples which specify the two different types. So I go, oh, and have you seen these before? Yes. If you ever took statistics and you have seen the bell-shaped curve is leaking areas on both ends, right? But the area under the bell-shaped curve is 1, which is 100% for probabilities. So the reason why we don't teach statistics the way we're supposed to teach statistics here is because we can't really make Calc2 prereq for statistics, which is why our statistics doesn't transfer to every institution. You don't get to transfer our stats to NGIT. You don't get to transfer it to every major at Rutgers. Some majors will take it, some majors will not. Because if you need a calculus-based statistics, where you're going to use what we just learned here to calculate z-scores, t-scores, and other stuff that in your stats class, you get a table. What do you think those numbers came from? They all came from the integral, which is a z-score cutoff point is one limit, and infinity or negative infinity is the other limit. And the entire chart of z-scores and t-scores is generated by working out each one of those integrals from Calc2. So,
my stats professor where those numbers came from and said he didn't know.
So z-score over here, and if you want area to the left, that's negative infinity to your z-score of 1.68. It's just the integral from negative infinity to 1.68. And then there is the function over here for the bell-shaped curve, which is actually to the negative x squared of a form. You have something with a standard deviation to normalize it here. I can't remember, like 1 over 2 sigma, I think, dx. There is a function involved. Anyway, that's not important. Important is to know that the entire thing is derived from what we are learning tonight. And if you're having a stats class that is calculus-based class, that's why. And if you're wondering, you know, going to a school why they're not accepting for transfer, that's the reason, right? you will relearn stats at the 4 years. So some 4 years will take our stats because they're not math, right? The Kane University, right? They're not math school. All right, let's go and take a look at some of these exercises from homework. So this one looks cool. 1 to infinity, 3x squared plus 1 divided by x cubed plus x dx. Immediately we know it's type 1 because we can see the infinity, right? You use your eyes, you look at it, and you see infinity. It's type 1. Step 1 is to do the